All right, number 4. A treasure map gives directions to the location of buried treasure. It begins at the entrance to an open field, and the directions are 10 meters due north, 15 meters at 30 degrees east of north, 8 meters at 20 degrees west of north, and finally 12 meters south of west. Sounds like I have several different vectors. Now, part of me suggests, we just kind of get a quick look at what we're supposed to be exploring here. So I'm going to put a coordinate system here just for funsies and kind of show you the way I see this. But then I'm also going to say to you, you have a method, let's try the method. All right? So it says 10 meters due north. So I'm going to have to kind of keep these small for this to work. 10 meters due north. So 10 meters due north. And then 15 meters, 30 degrees east of north. 15 meters, 30 degrees east of north. That look good to you guys? East of north, 30 degrees, a little bit longer than the last one. Let me see. 8 meters, 20 degrees west of north. Alrighty. 8, 20 degrees west of north. And finally, 12 meters south of west. There's no angle there. So 45, yeah. That's kind of what I see, right? Is that what you see? It's going to be something like that. So it's like a question mark. Okay. I haven't done anything, but I'll answer your question. Without an angle there, then we assume things like southwest and northeast are 45. But you didn't have that knowledge. So perhaps that was a stumbling block, and if that was it, that's fine. And I could stop here, or I could continue. It's your call. Okay. Now, what I had said to you guys to do is to convert all polar to rectangular coordinates, add all like components, and then convert your resultant back to polar. So there are 1, 2, 3, 4 vectors that have to be added together. So 1, 2, 3, 4 vectors that have to be added together. I don't know whether you want me to do it this way or not. I could do it in terms of north, south, east, west, or I can convert everything to x and y. I'm going to go ahead and just convert things to x and y. I have labeled the positive x and the positive y. So, but my first vector is, 10 meters due north. No, I'm not going to write out meters. What am I doing? 10 meters north. And I'm going to convert that to x and y. My second one is 15 meters, 30 degrees east of north. My next vector is 8 meters, 20 degrees west of north. And my last one, 12 meters south of west. There are my 4 vectors. Now, I don't see me having to do any work for the first vector since it's due north. I'm going to say it's 0 in the x and 10 due north. Is that all right with all of you? All right. Well, I have 3 others that I'm going to have to do. So let's start with the 15. And I'm probably doing this with more steps than are necessary for some of you. But that's okay with me. I'm trying to make sure that everybody understands. So I take each vector independently and figure out their components. So it's 15, and it's east of north, 30 degrees east of north. So it looks something like that. I'm going to choose components based on the fact that that's where the 30 degrees goes, and this is 15. So I think the components I choose will be a triangle that does this. That all good? I think I'd like to advance a few of the steps along, if that's okay. So like this is going to be 15 sine 30, or 7.5. And this one is going to be 15 cosine 30. I don't know what that is, but I'm sure with a calculator I could figure it out. I got 12.99. No, I'm doing the trig a little bit faster now because I've gotten better because I've been practicing, just like you guys, right? So now I can apply the fact that these are both in the positive directions of their respective coordinate. So 7.5 and 12.99, and they are both positive. Any question about that? We're going on to vector 3. Oops. Based on my recollection of vector 3, it's going to be on the other side, so I drew it a little different. So let's see, I'm going to start with, it's 8 units, but it is 20 degrees west of north. That look good to all of you? Any question about what I drew? This is 8, 20 degrees west of north. So I start at the north, turn towards the west, 20 degrees. Yes? Alrighty. I need to break that up into components. Those feel like, oh, I didn't want to do that. Those look good to me, don't they? They look good to you? So all of you hastily writing either didn't do this or did it way wrong, but no surprises here. This is the adjacent side. This is the opposite side. So this one's 8 sine 20, and this one is 8 cosine 20. So let's see, 8 times 20 sine, got 2.7. And I got 8 cosine, 7.518. There we go. I need to translate this into x and y. So it looks like it's in the negative x direction and positive y direction. So positive 7.518, negative 2.736. By the way, I'm still doing step 1. Convert all vectors from polar to rectangular. I got one more to do, but I'm kind of out of space, so I'm going to do it up here. Oops. Try that again. So it's set 45 south of west, so I'm just kind of making a quadrant 3 kind of look to it. Is that all right? So I'm going to draw myself a solid vector. Boom, right? Oh, that's way big. Okay. There we go. Make them a little smaller. And I need 2 components here. It doesn't really matter where I draw these because it's 45 degrees. So they're both going to be the same. But this sucker and this sucker. And this is 45 degrees. This is 12. This is opposite. This is adjacent. So this is going to be 12 sine 45. And this one's going to be 12 cosine 45. I only have to do this one once, right? It's going to be the same. So 12 times 45 cosine gives me 8.48. And this one's also going to be 8.48. Well, 8.485 there. They're both in the negative direction for their respective coordinates. So negative 8.485, negative 8.485. I have successfully converted all of my vectors from rectangular to from polar to rectangular. Step 1 complete. It's laborious, I know. Hard? No. Step 2, add up like components. Alrighty. So that's going to be 0 plus 7.5 minus 2.736 minus 8.485. Negative 3.721. My addition okay? All right. 10 plus 12.99 plus 7.518 minus 8.485 equals 22.023. This is in the x hat direction. This is in the y hat direction. Any questions about my answer? This is the resultant vector. This is where I'm going to go. So I have finished step 2. Go on to step 3. Okay. Here's where I pause and say, did you write anything in yours that looks anything more than what this gobbledygook looks like right here? Because if you wrote yourself nothing else, do you have any way of figuring out what you did later tonight when you're looking at your notes when I say at the end of class, prepare for your quiz tomorrow? You understand what I'm saying? If there's something you didn't understand and it became clarified through our conversation here, are you writing down something now that tells you what you did? Or later you're going to come to me and say, I don't understand any of this, Mr. Shelton. Will you help me? Because when I say what's in your notes, it should tell you stuff. Draw a little coordinate system, and then I drew the directions, and then I put a triangle around it. Those directions. All right. I can only ask you to do these kinds of things a couple of times, but my last step is to find my result. So I'm going to do that. I'm going to find my result. I'm going to get that out of my way, and I'm going to draw in a new coordinate system. I don't need much of one, and it appears to be in the second quadrant. So I'm going to draw it kind of like that, and I have 2 component vectors. One of them goes straight up in the y direction. And that's 22.023. And one of them goes this way in the x direction. These are not drawn to scale. 3.721. You have to construct a triangle from this. Don't do this. That will be wrong. That's not where we're going. So I'm either going to construct that triangle by moving this guy over, or I'm going to construct that triangle by moving this guy up. It makes no difference. It's the same freaking problem. So I'm just going to leave it the way it is right now. Is that all right for all of you? So my result is a triangle that starts at the origin, goes there. I need the angle, and I need the distance. Well, you guys can do the distance, right? You've been doing that since the first day I said we would have to do triangles. All of you knew how to use the Pythagorean theorem. So what's left is to figure out the angle here. I'm thinking based on this being my angle, that's my hypotenuse, this is the adjacent, that's the opposite. Then I'm going to look at tangent of theta equals 3.721 divided by 22.023. So my theta I got 9.6 degrees. Don't know what you got, but somebody tell me what the height is, will ya? Don't make me do any more work. I've done all the work. 22.3? Yay. So what's my actual answer? 22.3 meters at an angle of 9.6 degrees west of north. My original vectors were given to me in terms of north, south, east, and west. I need to give my answer in terms of north, south, east, and west. Yeah. All right. Mr. Shelton is relenting, and he's going to do one more because he's just such a swell guy. A runway is due north. A plane must maintain a speed of 75 meters per second in order to land. There's a crosswind blowing 25 meters per second, 50 degrees north of west. What direction should the plane point in order to successfully land? And how fast will the plane be traveling when it hits the ground? All right. Sounds like I have two vectors on this one. And let's see, the plane, it's 50 degrees north of west. Okay. So I have the plane, which flies at 75 meters per second, but we don't know the angle. And we have the wind, which is 25 meters per second at an angle of 50 degrees north of west. I'm going to establish a coordinate system that is centered on the runway. Doesn't really matter where I put this coordinate system. I put it in the middle of the runway. I can put it, at the end of the runway. The plane is going to be going north when it hits the runway. I just need something for reference. So that's my reference. That's north. I know everything about the wind, so I'm going to draw the wind in. The wind is 25 meters per second at an angle of 50 degrees north of west. That's the wind. That all good for you guys? It's a little bit large, but I want to make sure you can see it from where you're sitting. Based on the angle that was given, this is 50 degrees because it said north of west. Any question about that? All righty. I think the plane is going to have to be going that way to counter the wind. Would everybody agree with that statement? I know its speed will be 75 meters per second, but I don't know the angle. That one is, an unknown. So I understand that at the very end of this problem, though, the plane has to go this way, right? That's the whole point. So the plane can have no x velocity when relative to the ground. So here we go. I'm going to go ahead and label this the positive x direction, this the positive y direction, and this the negative x direction. Just to shake things up a little bit, remind us that positive and negative is arbitrary. That all okay with you guys? All right. I need two components here to describe the wind, so I'm going to convert it first. I'm going to use that component and that component to describe the wind. I'm going to make a triangle that frames the angle that I was given that is aligned with my coordinate system. I'm saying these steps out loud for two reasons. One, so I'm going to remind myself that the plane has a velocity of 25. I'm going to orient my triangle here by saying this is my right triangle, this is the opposite side, and this is the adjacent side. I'm going to do my trig now. And I hate to do this, but again, I want to make sure nobody can say to me later, you never taught me this. Sine of 50 has to equal opposite over hypotenuse, and cosine of 50 has to equal adjacent over hypotenuse. Right? This is where we're getting that stuff from the last problem, in case you didn't know. So opposite is 25 sine 50, and adjacent is 25 cosine 50. X and y, so let's do the plane here. 25 times 50 sine. Get 19.15, and that's in the y direction. And then 25 times cosine 50. Oh, did something wrong there. 25 times cosine 50, 16. Those are my two components. Any questions about that? Yeah. I'm going to keep going if that's all right with you guys. Are we all right? It doesn't really matter where I draw my components for the next one because I don't have the angle. But because of the way I've kind of mashed this up on the screen, I'm going to use this angle. That all right with you guys? That's how I'm going to lay it out there. So that means I have this component and I have this component. Those look like two good components. Based on that, we know the plane is 75 meters per second. That's the hypotenuse. This is the opposite side. This is the adjacent side. If I want to do the trig on this, the opposite side is going to go with sine, and the adjacent side is going to go with cosine. I don't want to do the trig like this. Again, I'm doing this for somebody else's benefit. Sine of theta equals opposite over 75. Cosine of theta equals adjacent over 75. So opposite equals 75 sine theta, and adjacent equals 75 cosine theta. We all good? Excellent. I'm going to write those in the chart, but I have to apply direction to those answers. So adjacent is my y. All right, so I was talking about adjacent, right? And now I'm moving on to opposite. So that'll be 75 sine theta, but it's in the negative x direction. I'm going ridiculously slow, but all right. Now, here's where I have to be thoughtful. I have done step one. I have converted all of my vectors from polar to rectangular. I don't really have answers for the plane, but I know something about the plane that I can apply. I know that the result, the answer, has to have no component in the x direction because the plane has to have a ground speed that is just in the y direction. So I'm going to zero out the sum in the x direction. That's going to help me find out what the angle is. So let's do that. Negative 75 sine theta plus 16.07 equals 0. I am doing step 2, which if you wrote it down says add up like components. This is like components. Can't add this one up because I don't know what it equals yet. So I have enough information to solve for theta now. So sine theta equals 16.07 divided by 75. Think I can get my angle now. So 16.07, oops, 16.07, bye-bye, Peter. Inverse sine theta equals 12.37. We good so far? I'm doing this deliberately slow, but because I don't want to do this ever again. I hate this garbage. This isn't any fun for me. So I know, well, I'm not sure if any of this will ever be fun for you guys, but that's my angle now. That's got to go right there. So because I'm lazy, I'm not rewriting anything. I'm just going to write 12.37 there. This goes back to, how many decimal points should I keep? Well, I've got 12.3725 blah, blah, blah in my calculator right now. I'm going to use all of that. But you know, do what you got to do. So 75 times plus 19.15, I get 92.4 meters per second. Now, what does this mean? Well, this is the result for the plane. This is what the plane is doing. The plane is going to have a ground speed. This is what the plane is traveling relative to the ground, with no component in the x direction and all component in the y direction. So my actual answer should be 92.4 meters per second due north, because my answer is in the positive y direction. All right, still a vector. But the plane has to point 12.37 degrees east of north in order to actually have a ground speed that is due north. Right, so the plane's not pointing due north. The plane is pointing 12 degrees to the east. But its ground speed is due north. We all good there? All righty. Projectiles. And I'm going to say this very clearly so that we have an understanding. There's a definition for projectiles that is largely incorrect in reality, but this is what we're going to do for projectiles in here. Projectiles are objects that move in 2 dimensions, but only experience an acceleration in 1 dimension. That's the definition of a projectile. So I'll say that a couple more times. To give you an idea of how we deal with a projectile, I want to remind you that we have rules of kinematics already in place that state that objects experiencing Earth's gravitational field will travel with an acceleration due to gravity of 9.8 or 10 meters per second squared downwards. So if I were to launch an object off of the top of, say, a balcony, the moment the object is launched, it has 2 independent velocities. It has a velocity in the x direction and a velocity in the y direction. I'm going to call this the launch velocity. I'm going to put v naught next to it. It represents the actual speed that the object is leaving. However, there are 2 components that describe its direction because it's being launched at a launch angle. We generally make the launch angle of a projectile the angle that is aligned with the horizon. Does everyone understand? So if we set the horizon to be the x direction, then that makes this Vx, because it is the horizontal velocity. It is along the horizon. But we will label this other one Vy, because it's in the y direction, but we'll put a little naught next to it. The naught symbolizes that this is the launch velocity. And it's how much velocity the object has in the y direction. Because gravity is acting in only one direction, right? Gravity is acting downwards, 10 meters per second squared. So that's going to be the acceleration of the object throughout the course of its motion. Now, once the object is launched, it's going to travel in some kind of path, and I don't think the path being curved is a bit of a surprise. Anybody who's ever thrown something probably has watched something travel in that path. I'm not going to say it's a parabola, but I think in the next day or two we'll prove it. But I want you to think about several places that this object is going to be over the next few seconds. It's a projectile, which means it's traveling in 2 dimensions, but is experiencing an acceleration in only 1 dimension. It's clearly experiencing that acceleration in the y direction, which means that this object's horizontal velocity never changes. Right? There's no horizontal acceleration. So whatever its horizontal velocity is at launch will be its horizontal velocity for the entire trip. Everybody understand? That's why there's no little knot here next to Vx. Vx is not experiencing an acceleration. Now, the y direction is. After a few moments of it being in the air, it will experience gravity. And because it will experience gravity, its y velocity will change. So after a moment, the y velocity will be less. In fact, pretty sure there will be a time when the y velocity is 0. The object's velocity is not 0, but the y component of the velocity will be 0. That's when it's at its maximum height. In fact, that'd be good information to have in your old notes there, right? Just like before, when the y velocity is 0, it's at its maximum height. It's not getting any higher. It's going to start to get lower. Of course, it will eventually turn downwards and have a downwards y velocity. And given long enough, that y velocity could become pretty big. But remember, these are components. These are components. At any one time, the object only has one velocity. Right? At any one time, it only has one velocity. These are the components of its velocity. One of the components is changing. One of the components is staying the same. That's a projectile. The reason we study projectiles is because we can get a pretty good estimate for how projectiles behave with or without air resistance by doing this kind of processing. And what I want you to do is a simple chart. When faced with a projectile motion problem, I want you to create a T-chart. And I want you to label one side the vertical side, C-A-L or C-L-E. Is it vertical or vertical? I'm going to leave it like this. It's going to be cal today. Tomorrow it could be col. I don't know. Actually, I'll probably just put a V tomorrow. And horizontal. Now, this should be obvious, but I don't think it is. In the vertical, I've got delta y, right? Change in the y position, so y displacement. I've got vy initial, vy, a, and t. Right? All the things that I would associate with uniform accelerated motion. But in the horizontal direction, I've got range, which is what we also call delta x. Where it lands is called the range. But it is the horizontal displacement. We have a horizontal velocity, vx. But there's no acceleration. So remember, when you take acceleration out, you don't have much to deal with, right? It just becomes range equals vx times t. If there's no acceleration, how far you go depends on your speed and time, and that's it. This side, well, you have access to all those motion equations, right? All 5 motion variables, and we're dealing with an acceleration. Generally, our acceleration is gravity. Could be gravity on the moon, so don't get complacent. But I also want you to know something. It travels up and down in the same amount of time it takes to go side to side. So every time I draw this chart, you'll see me draw this arrow like that, this little curvy arrow to remind you that the time on one side has to be the time on the other. Every single projectile motion problem generally has you figure out time using one side of this chart. And if you've been paying attention to kinematics, you know you need 3 pieces of information over here to figure out time. Or 2 pieces on this side to figure out time. We all good? What I did not get a chance to talk to you about, which you should figure out, is how are these things related? How is the angle and launch velocity related to the y velocity and the x velocity? Probably some trig in there, right? Something with sine theta and cosine theta. All right. The bell rings in like a minute.